seniors kind of tend to lose focus towards the end of the semester, whether they're going to maybe be graduating. So realize that our last two labs will be 11 and 12, and those are Simulink simulations. Now with Simulink, you never quite know what's going to happen. They could have upgraded Simulink and now some stuff broke. The programs you have worked last semester, but there's no guarantee. In addition, some of you guys have your own installations of Simulink on your own PC. No guarantee it's going to work on that version that you have. So if I were you, I would start thinking about that at least. Maybe start putting together the Simulink ahead of time just to see what you're up against here. If you put it together and it works, you can just kind of forget about it maybe and wait. But I would start at least thinking about that possibility that you may run into problems. Not wait till the last minute on the Simulink stuff. All right, frequency shift keying. Pretty easy to understand when you look at the time domain signals, kind of like the FM wave. We're making a binary decision though, so it's a lot simpler. So if we use, this is the one we're going to use as our message in the lab. If we have that as our message, then our, high amplitude, high frequency, low amplitude, low frequency. So we're basically going back and forth between two frequencies here. This is all supposed to be the same amplitude, by the way, but I can't do that very well. So there's the FSK wave. Pretty easy to understand this concept, high amplitude, high frequency, low amplitude, low frequency. The spectrum as well, I'm going to put it down here. Similar to our OOC, as I told you at the time, OOC was kind of a special case of FSK. You end up getting this. That spectrum, HD sync ND, at these two frequencies. Remember, OOC was, frequency F1 was 0 hertz. And we either have carrier or nothing. So this is a little different, but not too far off from OOC. So there's the way FSK looks. Let's go through and I'll walk you through the pre-lab, and then your job is to just fill in the rest of the details. Because if I don't do this, almost nobody understands how to do the pre-lab. So we're given our message here, two amplitudes here, plus 0.4 of a volt and minus 0.4 of a volt. A quantity called F sub D is equal to 134, where is it? 134 kilohertz. This F sub D number, that's something we're going to figure out tonight. Each bench has a different F sub D, and that'll be part of tonight's lab, so you'll understand more about that. But just for this problem, we have to have an F sub D value, so we'll just use that one the whole class. All right. Carrier frequency we're given as 500 kilohertz. Message frequency 10 kilohertz. Okay, so let's use this now to proceed. So part 1A of the pre-lab, max frequency deviation. And it's defined as delta omega. This, by the way, is 2 pi times F sub D for delta omega times the maximum part of our message, absolute value of the message. So, this, we understand how frequency modulation works. High amplitude, high frequency, low amplitude, lower frequency. It just varies depending on the amplitude of the message. So this is basically saying what's the most you're going to deviate from the carrier? We're at the carrier when there's no message, and then as the message amplitude comes, we go higher or lower in frequency depending on what that amplitude is. So just like we see here. If we were here at 0 on the message, we got pure carrier. We go high amplitude, go to high frequency, low, we go to low. So this deviation is just going to be, here it's symmetric, plus or minus 0.4 tenths of a volt. So this is just going to be, what's the most we're going to deviate from the carrier is what this wants to know. All right, so this is just going to be 2 pi f sub d, that's delta omega, times, 4 tenths of a volt is what our message is the farthest it gets away. So you guys can figure out what that number is. All right, the next part, frequency deviation. So this is the maximum frequency deviation. Now they want to just know, what is the frequency deviation? So this is not just one number. This is going to be a plot with time. Frequency and what it changes, how it changes with time. Well, you look at this, this is just a scaled version of the message, isn't it? So the plot's going to look just like that. But that's in voltage amplitude. We're going to be converting to frequency. Another way we can describe this is the derivative with respect to time of what we call the phase deviation. Phi of t. And that shouldn't surprise us because we know that frequency is the derivative of phase with respect to time. So the frequency deviation is equal to the derivative of the phase deviation with respect to time. So we know it's going to look like that. So we can make a plot here with time that looks the same way. By the way, we're given what these frequencies are here. So if this is 0, this is in milliseconds, this is 0.05 and 0.1 millisecond period. I forgot to write that in. So when you do these other plots that I'm not filling in this information, you'll fill in the right time axis and the right amplitude axis, X and Y axis, whatever they happen to be. All right, so this is going to be equal to 2 pi f sub d, because that quantity right there is our delta omega, right, times m of t. So you can see we're going to be going here from 2 pi f sub d times 0.4 down here to 2 pi f sub d minus 4 tenths of a volt in frequency. And if you look at this, you can see that the 0 line right here, now we're on frequency scale on this x-axis, I'm sorry, in the y-axis. That 0 point in amplitude here is the carrier frequency. We're relative to the carrier here. So if this is the carrier here, we're going above the carrier in frequency, to that frequency right there. And then we're going below the carrier by that much frequency. So this is a relative plot, relative to the carrier. So that's our frequency deviation. So once again, you guys fill in the numbers, calculate what these are, and label correctly. All right, 1C. Now it's asking for the instantaneous frequency. And this is carrier frequency plus the derivative of the phase deviation or the frequency deviation. So this right here is just this guy. And then it's carrier added to it. So it's like giving this a DC offset, isn't it? So it's like we have a DC offset here, which is the carrier frequency, 500 kilohertz. And then we have riding on top of this thing, now DC offset, that same plot we have over there. So while this was relative to the carrier, now this is an absolute plot. So now we're going carrier frequency plus 2 pi f sub d 4/10 of a volt to carrier frequency minus 2 pi f sub d 4/10 of a volt. So now this is our absolute frequency about the carrier, which we've now included in this. So once again, a relative plot and an absolute plot. How the frequency is varying. Once again, your job, calculate all this out and label properly in time and in frequency. All right, next, 1D, the phase deviation. So in other words, now we're going to be taking the integral of this guy, because there's the derivative of the phase deviation. If we just want the plain phase deviation, we got to back this derivative out by taking the integral of that guy. And you can kind of see what's going to happen here. As we take the integral over this positive part, we're going to go up to a peak, and then as we go over the negative part, it'll go back down to 0 again. So we have our, like a triangle wave again. We've kind of seen this before, haven't we? So it's going to look something like this, the phase deviation. So I'll let you guys figure out what that peak is there. And you would just do that by taking the integral from whatever time that is to whatever that time is of this area. We know, what that height is. Figure out what that is. Label that properly. The FSK wave, part 1E, well, that's just that, a sketch of the FSK wave. All you got to do is label it. Label what these frequencies are, F1 and F2. Part 1F, the two-sided amplitude spectrum of P of T, or actually M of T. This thing. Well, that's just HD sync ND, isn't it? Half duty cycle. Notice though that it's got no DC offset, so that means the spike at 0 is not there. That's the only difference. So just for part 1F, it's just HD sync ND on this guy. Duty cycle 1/2. No spike at 0. Normally we have a DC offset here. It's not here now. That's the one exception. You guys should be good at HD sync ND by now. Experts. And then the last one, part 1G. Here's part 1G right here. Sketch the FSK spectrum. Just label properly. So you should be able to do the pre-lab. There's also asks about how to do a simple detector, just like the one you just turned in, basically. We'll actually use it tonight and do that for our FM lab. So that second part will be trivial like the first one was, just understanding how we have a much simpler decision here. With FM in our detector, we had an analog decision. It's probably not even called a decision. We're decoding an analog signal. Here, we have a binary decision. That just makes things much simpler. And that's why F sub D isn't so important for this case. Well, it is for tonight's lab. Understanding how you decode this stuff is so important. I gotta just do a little sketch of it on the board so you get it in your head. Because it's the basis of all digital receivers. Okay? How do you decode something like this? Very, very simple concept. Here's the kind of a real easy way to view it. Of course, it's more complex than this, but the concept you need to understand. If you understand this concept, it'll be easy for you to understand the basis of all digital receivers used today, and most receivers are digital. We have one leg, we have our signal split, we have one leg coming down here to multiply and accumulate them. This is a correlation operation in hardware. We have frequency F1 here. Here we have frequency F2 here. So we've got two legs. It's like, you know, frequency F1 is our zero decision. Frequency F2 is our one, the way we've laid it out. So that's the one leg and the zero leg. We're decoding ones and zeros here. Let's say we've got the high frequency one coming in over a bit width. So that's our high frequency one, and here's our low frequency one. If we correlate this one against the high frequency one, we know from our MAC operation lecture that that's going to be a high correlation output, isn't it? So we're going to get a big value here. When we correlate that guy against that guy, different frequencies, it's going to be small correlation, right? So we get a small result here for that particular bit width. And then we say, oh, I just got a 1 because that's where the bigger correlation led. See how simple that is? Now, you can see what's going to happen in the other case. What if a 0 comes in? Same thing again, over a bit width. We've got the low frequency one. We correlate against here, it's going to be a small correlation with those two different frequencies multiplying and accumulating. Here we're going to have a big one because it's the same thing. And we say, hey, we got a 0 that time. Just brute force and easy this is to decode digital data. It's complicated, of course, to get bit, you got to get synced on the bit. That's an acquisition process that's not trivial. But bottom line, digital receivers are full of banks of correlators doing this. Yeah, it's more than I'm showing you right now. That, like this would have 2 per side, right? Each leg would have an I and a Q, and we'd be doing this in quadrature, whatever. Just understand the basis. All we're doing is a bunch of correlations and seeing and making decisions. Which one's bigger? That's the bit we got. So you'll see. Where I work at JPL, we're in the tracking department, and the whole section is all on tracking and applications. And there's a lot of digital receivers being used for different things, but this is basically what's going on in all. Little details are different, but that's the heart of it. So make sure you understand that and get what's going on. Any questions on that? Just so simple, the concept. All right, so you should be good for the FSK pre-lab. Any last questions before we talk about tonight? The FM lab.